get a little harder. We're going to be finding right now greatest common divisors, which is a really nice little algorithm. My mind's a blank at the moment. Who did it? It's one of those Greeks. Here's what it says. No, I guess not. You said, I think. Yeah. All right, so we want to find the GCD of two numbers. So for example, if the input is 64 and 44, we want to find the greatest common divisor, which is an integer that divides into both of them and is as big as possible. So in this case, it happens to be 4. Right, everybody with me here? How many people have seen this algorithm before? A few of you? Right, so we need to think about what kind of steps you might take. In fact, let me tell you one thing about this algorithm. Remember I said most loop invariants fit into these various categories that we looked at? Well, this is a weird one. All right, so in fact, in some ways this should be a category of its own, because there are a lot of algorithms who I would say, their loop invariant is like this one. All right, so think about what kind of steps you might take. If you have A and B, and you subtract from A, you subtract B, one thing you can note is that the GCD doesn't change. Right? Because anything that divides into both A and B divides into A minus B and divides into B. Right? And similarly, if it divides into A minus B and B, then it divides into A into B. And so that's just a little useful thing. And so here's that example. Right? So anybody want to think about what loop invariant we're going to have? How about even you've seen the algorithm? You know the loop invariant? No.
That's Elder's fault.
That's Elder's fault. How could he show the loop invariant slides about the cards and not make sure you know the loop invariant? Did you even see these slides? No.
It's sort of like these ones, but...
Fair enough. All right.
Get a picture of them.
What?
Get a picture of them.
Oh, did you have a picture? Yeah, Euclid would be good to have a picture of. All right, so here's the loop invariant. We're going to maintain some values x and y. And the property that we want to have is that the GCD of x and y will equal the GCD of a and b. Right? Our goal, of course, originally is to find the GCD of a and b, but we kind of now have a new goal. Right? In some ways, this is kind of like recursion. Our new goal is to find the GCD of x and y because it's the same as what we're looking for. Everybody get that? Make sense? And what's our measure of progress? I mean, in general, what's sort of, why have we made progress going from here to here?
X and Y are smaller.
They're smaller, right? They're smaller. All right, so how do you maintain the loop invariant? Well, I have a value x and y, and I know their GCD is equal to GCD of a and b, and I replace them with x minus y and y, right? And then we want to, from the loop invariant, we had this, and so we continue on with that little rule, and see we maintain the loop invariant. Everybody kind of buy that?
So it doesn't know it's breaking the loop invariant until the end, because we have to keep on calling GCD, right? Or
well, we're not doing recursion here. All right, we'll be doing recursion in another day or two. In fact, GCD could easily be done by recursion.
yeah, but I mean, how does it know that it's equal? Because you have to run this. You have to run the GCD.
Yeah, well, that's the kind of amazing thing is that the loop invariant here doesn't say we know what the GCD is.
Okay, so that doesn't matter when you're making a loop invariant.
Yeah, we don't know what it is. All we know is that they're equal. Right? So here, how do you establish this loop invariant at the beginning? You get at the very top of the loop, you have A and B. How do you establish the loop invariant? Well, you need an x and a y for which this is true. Give me an x and a y such that the GCD of x and y is equal to the GCD of a and b. A and b, right?
Okay.
Right, that's the way you establish the loop invariant. In a real, often we want to establish the loop invariant in the most trivial way possible because we don't, we really are lazy. So, and then once we have an x and a y, then you replace the x and a y with this, and then you keep doing that, and we keep making progress while maintaining the loop invariant. Does that make sense? So, we make progress because it gets smaller. All right, so here's an example. We establish the loop invariant by setting the same, and then we subtracted off 44, and then we don't want to subtract off 44 again. Well, one thing about the GCD is you can swap them, right? So you swap them, you subtract. You swap them again, and you subtract, and then eventually, if they keep getting smaller, one of the numbers will end up being 0, right? Now, what's the GCD of 0 and 4? It's 4, because 4 divides into 0 and 4 divides into 4, right? And that gives us our answer. Everybody got the algorithm?
Should x being greater than or equal to y be part of the invariant as well? Because if that wasn't part of the invariant, then
you could put it part of your invariant, I suppose, but I think of it more as part of your step, so that if they're in the wrong way, you flip them and subtract. But it doesn't really matter. Something like that. All right, what's the running time of this algorithm? In fact, I was talking to somebody last class after everybody else left. Maybe they can tell us the running time of this algorithm. Do you think it's polytime? You think it's exponential? You think it's reasonably fast? Do you think you better not wait for lunch? How many think it's polytime? How many think it's exponential? How many people have no idea? All right, that's what we like. All right, so I'm going to argue actually that it's exponential time. All right, so here's an example. Anybody want to trace this example? No? So when I talk about the running time of an algorithm, the basic intuition is how much time does it take for me to give you the question versus how much time it takes you to do the question, right? How long does it take me to give you this question? Right? I can write a bunch of 9s down really pretty quickly, right? But you don't want to be tracing this out, right? Why? Well, because it takes a long time. You know what I'm saying? So, yeah. So now, you might argue here, well, the running time in this example is order A, right? And then you might say, well, order A sounds linear to me, right? This should be linear time. Now, I think I said this already at the beginning of the first day. Everybody in this room understands running time except for the one thing that we're going to say right now. And as a warning, I think I've put a question about this on every exam since the beginning of time, and usually about a third of the class gets it right, even though I'd say at this point in time this is going to be on the exam. They still get it wrong. All right, so for me this is important, right? Why is this a bad algorithm? You need to understand why this is a bad algorithm. So yes, the running time is A iterations, and that feels pretty linear. But the thing is, running time it says how much time does it take for you to do the computation as a function of the size of the input. All right? So, right, that's what it's saying. Function from size to time. How do we define size? Well, we can define it as the number of seconds that it takes for your machine to do it, how many hours it takes for you to do it by hand, how many lines of code gets executed. We could count additions maybe and say how many additions happen, how many subtractions happen. Does it matter which definition we use? Think it matters? No. No, it doesn't matter. And the reason it doesn't matter is because, as far as I'm concerned, we're going to be doing big O anyway, and the big O hides a constant, and there's more or less a constant between these. Everybody count, and it's a reasonable constant. Right? Maybe you can execute 5 billion lines of code per second, right? So there's a billion between this and this. But, I don't know, billions, it's for a theory, a person, a constant of a billion, who cares, right? What's a billion between friends? All right, so now, what's the size of this input? Here's an input. Anybody want to tell me its size? 1? 1's a good, reasonable, good guess. Is anything? How big is this? What do we want to measure it? Well, here's various options. We could measure it as the size of the piece of paper to write it down, right? Number of square inches. We could write it down as the number of bits to write it down. Turns out that it takes 17 bits. It takes 5 digits, and the value is 83,920. All right. So it doesn't matter which of these we use for size. How many people, which one do you think is the theoreticians of computer science use? They use the number of bits. Well, what's kind of nice about this one? Well, it's kind of, it's intuitive, right? Is there a constant between these? Yeah, you have a certain amount of area, you can put so many bits per square inch. Right, what about digits? Well, that one's intuitive, that one's formal. Digits is reasonable. The number of digits is, actually the number of bits is 3.32 times the number of digits. What about this guy? These, I say, are all the same within a constant. What about this guy? That guy's the big one, right? Wouldn't you agree that, 2, 17, 5, whatever, right? But 38,000, now I just said a minute ago that a billion wasn't a big deal. So, but the thing is, this one's going to grow exponentially fast, right? So the number of bits equals the log of the value, right? If you're doing number of bits, it's the log base 2. If you're doing it, if you want a number of digits, you do it base 10. Right, everybody with me here? So the value is exponential in the number of bits. Right? If I put, all I have to do is if I put another 0 here, that took me a constant extra work. Right? But if you're going to count up to that number, it's going to take you 10 times longer. You know what I'm saying? And then I put another 0. Oh, that wasn't a big deal for me, but now it went 10 times longer again for you. Right? You're starting to really sweat. All right, so this is what I kind of say is, as the size of this input, we could count the number of 9s, the number of bits, the size of the screen that we use. Right? All of those are reasonable. I could say it to you. We could talk about how many bits I need to send down a channel to ask you the question. Right? But for you to actually run this algorithm is going to take a long, long time. Right? So a classic example is, I love President's Choice Banking and I love their food. So when I bank online, somehow they have a 100-bit number, which is my security code, right? And I can send them my 100-bit number and they can send it back, and the evil people of the world can look at my 100-digit number. And why don't I care that they look at it? It's because they don't know how to factor it. Right? And factoring it, you should say factoring's easy. You give me a number n, I want to factor it, I divide it by 2, I divide it by 3, I divide it by 4, I can find what divides into n. Right? How long it's going to take me? It's only going to take me n time divide into n. Right? But if if n is the value and little n is the number of bits, right? And maybe the number of bits is 100, then the value is 2 to the 100. Right? And so I can send these 100 bits around with no sweat whatsoever. In fact, maybe it's probably not bits, it's probably bytes, isn't it? Because 2 to the 100 is too small. How about 2 to the 100 times 16 or times 32? That's getting a little scarier. Right? People follow what I'm saying here? So I'm going to, at some point, you can promise, I'm going to ask you what's the running time in this algorithm, and you should answer it's exponential in the size of the input. Alright? Alright, what's the size of the input? The size of the input, the number of digits, is log A. Right? So if the size is log A, what's the running time is a function of the size. It's 2 to the n. If n is the number of digits, or bits, then A is 2 to the n. Right? The running time is exponential in the number of the size of the input. Everybody with me here? Good. So we're going to speed up this algorithm. Here was our algorithm. We took x and we replaced it by x minus y, and then we kept doing that. How long can we do it? Well, we keep doing it until this becomes negative. Right? And then we swap. So what we want to do is from here, we want to go bang in one step to the point at which it becomes negative. Right? So what I is going to make this negative, right, is clearly going to be x divided by y. Right? And then what's you're going to get here when you subtract that many i's, you're going to get the remainder. Right? People buy that? So instead, we're going to skip all of this work. And we're going to go from xy straight to what is the remainder when you divide x by y. Right? People buy that? So what is the remainder? Well, another way of writing that is x mod y. And one property of x mod y is that it's always smaller than y. Right? So what should we do? We should automatically swap them. So the algorithm is starting from x and y, we replace it with y and x mod y. Alright, good? So here's an example. Okay, this kind of comes back to what you were saying. Uh-oh, we already have this number smaller, right? So should we do some extra code and work on swapping them? Or, other option is sometimes just run your code and see what happens. Alright? So if we run the code and see what happens is we put this, the y comes over here, and what we put over here is 44 mod 64. What's 44? You know, if you take 44 and you divide it by 64, it goes in 0 times with the remainder of 44. Right? So the step automatically flips them for you. You don't need any extra code whatsoever. And then you take 64 mod 44, you get 20. You get 44 mod 20, you get 4. 20 mod 4 is 0. And then we know the answer is 0. Right? Does that make sense? So here's another example, right? Which would have taken a long time with our previous algorithm. But here, you take the mod, you're already down to 2 here. Right? You take the mod down again, it comes down really quickly. And then we're good to go. Everybody happy there? So, what's the running time? Well, remember the size is of the input. It's kind of how many bits it takes to write down the input. Well, that's the log of the number to write down. It's the number to write down A and then plus the number to write down B. Right? And now we want to kind of calculate how many of these iterations we need. And if you want to form a more precise proof, it's in the book. But you're never going to be tested on it. So let me just give you a little intuition. you know, if you go, we need a measure of progress, right? And your measure of progress could be the sum of the numbers, it could be the product of the numbers, it could be the size of the first number. You know, you got to decide your measure. I'm thinking about the measure of progress being the first number, in which case in this, we did a step here, and we didn't really make very good progress, right? It was wimpy progress. But one thing that it's not too hard to prove is that wherever you are, if you do 2 iterations, you're guaranteed to divide the first number will come down by at least a factor of 2, every 2 iterations. And so if your first number comes down by a factor of 2 every iterations, then you need to do 2 iterations at most log a times, right? Because a divided by a divided by a, that's log a times. And so basically it's you know, not only is this new algorithm, so okay, so let's try it. What's the running time in this new algorithm? Is it polynomial? Is it logarithmic? Is it linear? Is it exponential? Anybody want to go for linear? Why do you go for linear?
It's the same.
Because it's the same, right? It's linear because the running time as a function of the size of the input is linear, right? In fact, as a general rule, you're rarely going to get algorithms that are faster than linear because, well, you got to at least look at the input, right? If the input matters, you got to look at it. So don't expect it to be faster than linear. Does that make sense? Everybody good with this algorithm?
Whenever you say log, you mean log base 2?
Good question. So this is going to come up a lot. If I care, I will make a point of saying what it is. Generally, I don't say what it is. And the reason is because I don't care. Right? Little modus ponens there. Right? Why don't I care is because I'm doing big O. And if I did here, if this was base 10 versus base 2, the difference would be a factor of, what was it, 3.31, I don't know, something like that, right? It doesn't matter what the base is. In fact, we're going to see later on, one example of logs is when we do resolving recurrence relations. And there it's really handy, the fact that it doesn't matter which base you use. And anyway, it doesn't matter. Good question, though. All right, so here's the code. It's as easy as easy, right? You give an A and B. The code establishes the loop invariant by setting x equals to A and y equals to B. Our loop invariant is, as I said, right? And if you got y, you stop and you answer x, and otherwise you just set the new x to be y and the new y to be x mod y, and life is really easy. Everybody good with that? All right, so when computer science sort of started, I don't know, maybe not when it was started, maybe it was after it was going oh well, in the 70s at least, you know, when, you know, I don't want to age myself here, but when I took computer science in high school, we had punch cards, all right? So, yeah, back then, what did most computers do? If you ask, what are computers spending their time doing? Anybody know what it was?
Calculating.
Those are pretty broad.
Recording time.
Surprisingly enough, most computers were spending their time sorting. I don't know why, that's what they needed to do. You know, they needed to sort. And when I took computer science, we spent so much time looking at sorting algorithms. But it's still kind of interesting to look at a lot of sorting algorithms, mainly because in this course our goal is to learn different algorithmic techniques, and sorting is a nice example of lots of algorithmic techniques. All right. Now, one thing that I have to do a few times a year is I have a stack of papers and I need to sort them. You know, they're your exams. I need to sort them, and so I developed this algorithm, which is, I find the best way, if you have a desk this big and you have a stack of papers and you want to sort them, this is the way to do it. All right? So the input is a pile of things to sort. and the output is you sorted them, and the requirements is that we want it to be easily executed by humans, let's say that you're only allowed to have 7 piles on your desk at a time, right? My desk is only so big. Actually, I usually do it on the floor anyway, but and what you can do is you can look at an exam and you can take it from one pile and put it in another pile, right? And we want it to be in login time. And yeah, this is the only one that you probably will ever run yourself. All right, so here's your input. This here means that these exams are in an arbitrary order, and they start with the letters from 1 to Z, right? Basically, it's all your exams. And one thing that I've heard was true is that you can think about 5 things at a time. Some people argue, oh, it's 7, but whatever. So I'm going to take these exams, and I'm going to look at the first letter of the last name, and I'm going to throw it into one of 3 buckets based on what the letter is. 5 buckets. Why 5? Because it makes the algorithm a little, 5's faster than 2, but I can think about 5 buckets. I can think about these groupings. All right, so that's what I do, is I go through the exams and I divide them into buckets. Everybody good? Then I take the buckets and I stack them up into, now we got is a stack of buckets. And they go like this, so you can separate one from the other, right? And we need a loop invariant. Anybody want me to tell you what the loop invariant is?
Stack size against 1.
Is that a loop invariant?
It's a step.
That's a measured progress, or it's an action, right? So what might the loop invariant be? Here's the picture, right? Proof by picture. The loop invariant is I have a stack of piles, and what's true about each pile is each pile sorted. No, wrong. Each pile is not sorted, but everybody in this pile comes later than everybody in this pile. Right? Does that make sense? All right. And I also have another pile over here, and they're sorted, and they go before everybody. All right? That's our loop invariant. So, and this final pile is upside down because I want to throw things on the backwards. All right, loop invariant. Now, how do you maintain the loop invariant? Well, I have a stack, I have these stacks of piles. I start with the first pile, and I divided it, what is this first pile? It's all exams that start with A to E, and so I throw them into 5 buckets, right? In the obvious way. And now, what do I do with these piles? I put them on the top, right? I just take these piles and I put them on the top here. Why is it?
Don't you have 10 piles there, and you said you can only have 7?
Oh yeah, but they're all in one spot on the table. They're like this.
Oh, okay.
Right? So yeah, piles. Good. He's smart ass. Yeah. So we only can have 7 stacks, and this is a stack of piles. All right, does that make sense? Right, so these guys here, we got too many of them, and so we stacked them up. And you'll note that we've maintained the loop invariant, right? We still have one stack of piles, and in each pile, everything comes before everybody in the next pile. Right? So we stack them up. Those are our piles now. And then what do? Is we take the A's, and this just says our loop invariant's true. Right? We take our A's, and we do it again according to the second letter. Right? And then we stack them up. And now we take the top pile, which is everybody in this, this range here, and what do we do with them? That's our loop invariant. Well, we would do that again, except we notice that the pile's really pretty small. Right? In fact, this usually happens before this stage. If I have in my hand a pile with only 5 exams or 6, I just sort them. Right? And when they're sorted, what do I do when they're sorted?
Put them in the sorted pile.
I put them over there in the sorted pile. So that's then so the loop invariance maintained, and then I get the next pile, and they go up, and the loop invariance maintained. Oh, and they're upside down, so I can pile them on top. I keep doing this. They go up there, then I do the B's, and right, and then I just keep going. Life is good, and everybody get the algorithm? All right, good. So let's do another algorithm. This one's called Radix sort, and back in the day when people had punch cards, they had to sort these punch cards, right? And these are cards, physical cards, right? This is not data. And they had a machine. Oh, right. So they have all these punch cards. One punch card has a certain number of columns, and each column is one digit. I think it was a digit base 16. And you wanted to sort these cards, right? What did you have? You have a bucket sorting machine, and you had a dial on the machine, and you set it to say the second digit. You say, I care about the second digit. Look, I didn't have the digit right in my brain. And you put it in the machine, and it goes, and it just moves the cards into the right one of 16 buckets, right? So it sorts them with respect to that digit. Everybody good? And another thing that's true about this sorting is we call it a stable sort. That means if you have two cards in your original ordering that have the same digit, then when they stay in the same order, right? You don't mess up things, change their order unnecessarily, right? And that makes sense. It's because the card comes, and then the next two is going to go on top of it. Everybody good at this? So now we want to sort these, right? We have all this stack of cards. We got our dial. We want to set our dial to some digit. Which digit do we clearly set it to? Everybody agree we set it to this digit here? Yeah? Have you been here before? No. Oh, well. Did you pick up on my clearly? Yeah, we're going to do this digit. All right, but let's first pretend we do that long digit. Which do we sort with respect to that? And now that looks already good, right? But this goes back to the pile thing. What happens if we now sort in respect to the second digit? What's going to happen? It's just going to mess everything up. And the only way you don't mess it up is somehow you keep these guys in piles, or maybe you have piles of piles like we did last one. But this poor, clearly it's going to be a woman, since this is a sexist age, and she's sitting in this little room and she's trying to do this, right? So we got to make her life easy. So we lost the meaning of sorting the first digits. Everybody kind of following what we're doing here? So for some reason, it seems completely weird to do this. We're going to sort with respect to the lowest digit number. All right? So there they are. We sorted with respect to the lowest digit number. And then we're going to sort it with respect to the second digit number. And what just happened? At least in this example, proof by example. Everybody see what's happening? The first two digits are sorted. Now, is that a proof? Not quite, right? You might not have believed that I did it right. That's proof by, just wait, that reminds me.
Poker.
We're going to have a break for station identification.
Poker?
Remember I told you that I had this thing here, and I wanted to show it to, and then I have this brother I just met. He's 20, and I only met him about a couple weeks ago. But anyway, I showed him this trick last night. He was very impressed. Right, you ready? Isn't that fun?
Do it again.
Do it again. You got to really shove the cloth in there. Isn't that fun?
Yeah.
I learned how to do this in Thailand. Thailand is a great place to go.
Can I see your phone? No.
Yes.
Okay. Oh, it's a fake thumb.
It's a fake thumb, isn't that great? All right. So proof by magic. We got these sorted, right? And we need a loop invariant. What do you think our loop invariant is going to be? What's true about this data?
It's stable.
Hmm?
Because it's stable, it stays sorted.
Yeah, so we just want to picture. State again has a sort of an action sound to it. We want to say, give me a statement what's true about this data.
First two digits are sorted.
First two digits are sorted. Exactly. And we had various types of loop invariants, right? Remember, we had more of the input, more of the output, reducing the search space. Is this one of those? No, so it's not more of the output, it's... What do we got? Think of what's more of the input. The more of the input is, you've read a certain amount of the input, right? How much have we read? We've read the first two columns. You pretend that the input is what you've read, right? And you have the answer, right? We've considered the first two rows, first two columns, and if you consider those first two columns, we have the answer. We've had them sorted. Everybody kind of buy that? All right. So that's what our loop invariant is, that we've read I of the inputs, and with respect to those, the cards are sorted. And so then we take a step, and what's the clearest step we take? We sort with respect to the I plus first digit, and we need to prove that we've maintained the loop invariant, right? It's funny, I always want to, when it's not go, I point it over here, but really I guess I should be pointing it over here, isn't it? Sort of counterintuitive. All right, how do we prove that we maintain the loop invariant? Well, we need to prove that it's sorted with respect to now the I plus 1 digits. And how do we do that? Well, let's take the cards and break them into these blocks like this, right? And one way to prove that the cards are sorted is we're going to take two arbitrary cards and we're going to prove that they're in the right order, right? And if we can do that, if we can say for any two cards they're in the right order, then what do we know? We know they're sorted. Does that make sense? Everybody with me here? All right, so we take two arbitrary cards, this card and this card, and if they're indifferent, if their first digit's different, how do we know they're in the right order?
Small ones on top.
Yeah, because we just sorted with respect to this digit, and if the first digit's different, then they're in the right order. Everybody happy with that? Now, other case is that the first digit's the same, and if the first digit's the same, then since when we sorted this column, it did it as a stable sort, so they're in the same order that they were before, right? But by our loop invariant, before we sorted, they were in the right order. Everybody follow that? Yeah? Yeah? No? Everybody good? Some people in a panic? Who's in a panic about this entire course? Good. Well, you guys should be speaking up more, right? You do pretty well, but you know when you don't understand something, you know, ask a question, and that, if nothing else, it gives all your buddies in here a chance to breathe and think for a minute, right? And if you don't understand something, they're not going to understand it too. People kind of get this proof? And you understand how this is the classic, this is exactly what loop invariant proofs are about, right? Loop invariant proof says we're at the top of the loop, we know that the loop invariant is true, that it's sorted with respect to the first I digits, right? So then we take a step. What is our step? Is we sort with respect to the I plus first digit. Now we want to prove that it's sorted, that the loop invariant is maintained. It's sorted with respect to the first I plus 1 digits. How do you do that? Well, you have to prove it's sorted. Well, it's hard to think about all of them. Are they all in the right order? Right? That's hard for me to think about. So let's think about pairs of them. I don't want to know if they're consecutive, whether they're next to each other. You know, that's hard. I want to think locally. These two cards, are these two cards in the right order or not? Right? If I do that for every pair of cards, then they've got to be sorted. Right? So two cards, if their first digits are different, then by the step, I sorted them. Right? And if their first digits are the same, then by the fact that I sorted them with a stable sort, kept them in the same order. Right? And then, by the fact that the loop invariant was true when I started, the first I digits, they were sorted with respect to the first I digits, so they were in the right order. Everybody got that? Sometimes if you just say, hey, I didn't really get it, and I say it again, you don't understand it the second time either. But sometimes it helps. Everybody kind of following what we're doing here? And let me give you another reminder of how I'm going to be testing you. You know, there's some chance, the chance that this algorithm is on an exam is pretty well nil. Pretty well nil, right? But the chance that there's going to be some problem where you have to follow those steps, you know, what's the loop invariant, what's the step, how do I maintain the loop invariant, chance of that is pretty much 100, right? The chance that the algorithm that we, you know, and in fact often, you know, I'll ask you to do a problem and I'm like, oh, man, are they going to get that loop invariant? Are they going to get it? No, maybe not, maybe. I don't know. I never know if you're going to get it or not. So if I'm panicking, I'll give a little hint, right? And there's a really good chance that the hint will be, you know, remember radix sort, right? I'm not saying that we're doing the radix sort problem, but, you know, it might make you think of that kind of loop invariant, right? Or I might say, well, think of more of the input kind of, you know, and so this is a, you know, I think every third year I say, think of radix sort. It's a good one.
Is this the third year?
All right, counting sort on the other hand, we'll do it kind of fast because, you know, it's actually just kind of dumb. But maybe not. Maybe it's cute. It's cute too. All right. So, but we'll do it. Counting sort is we got digits that we want to sort, and the advantage of the difference is that in this case, everything you want to sort is either a 0, 1, or a 2, or a 3. Right? The range is really small. And you want to sort them. So that's the input, and the output is them sorted. Right? But of course we want a stable sort. Remember what a stable sort is? Is that this 0, you know it's not a 0. It's a 0 followed, it's carrying along with it a lot of data. Right? So this 0 and this 0 are not the same. And they matter what order, you know, ultimately they're treated to be different. So we want it to be stable, that these two zeros have to end up in the same order that they were in before. Everybody good with that? And by the name counting sort, we're going to do it by counting, right? So, that's what I said about stable sort. Right now, let's think about the fourth record in the input with the digit 1. Right? 1, 2, 3, 4. Fourth digit. Where does it go?
1, 2, 3, 4.
It goes there. Right? And you notice how I got that? I counted. That's why we call it counting sort. Right? In fact, more precisely, where does it go? It belongs at index 8. Right? Why does it belong in index 8? Well, note I started the indexes with 0. And why did I start them with 0? Because it goes in index 8 because there are 8 guys that go before it. Right? The guy in index 0, for example, goes in 0 because there's 0 guys before it? Oh, all right. Thank you. You're good. All right, so how many people go before it? How many records go before it? Well, there are 5 zeros and there are 3 ones before it, right? So we want to count how many there of each guy, right? So we start with a table with, with indexed by the numbers that we're looking for, and we want to count how many zeros are there, how many ones, how many twos, right? And let's think. Everybody, think quickly here. How long does it take to count these, right? If I go through here, 1, 2, 3, 4, 5, 6. How many times does it take me to count the ones? They're in records, in time, but I have k different values. So how long does it take me?
K times n.
K times n. K times n. Is that good enough? No, that's sucky. How do we do it faster? I'm going to go through the list once. And when I'm here, what do I want? What's my loop invariant?
Everything counted.
I got them counted, right? It's got more of the input. Assuming that what I've read so far is the input, I have the answer. Right? Does that make sense? And then when I get the next digit, I increment the correct guy. Right? Right? So you count it as you go. That's kind of what I said. All right, so now we want to know how many records are smaller or equal to each value. How many records are smaller or equal to 2? Right? What's this plus this? Right? So to get this, I take this plus this and I put it there. Right? How much to get this? I go this plus this plus this and I put it there. Right? There are k of these. So how many times is it going to take me to do this?
K times.
It's going to take me 1 plus 2 plus 3 plus 4, k squared time. Right? People buy that? No? How do you do it faster? Well, if everybody the algorithm I gave definitely is order k squared. Right? Here, how many go before this 0? How many go before this? It's this. How many go before this? This plus this. How many go before this? This plus this plus this. Right? You add that up, it's going to be k squared over 2. Right? How do we do it faster? What?
Do one at a time, and then use the sum from the previous one.
Exactly. Exactly. Right? This, let's see how we're doing it here. This is, I don't think we've gotten up there. This is the k squared algorithm. Right, so here, this number is the sum of this number and this number. Right? It's the number that go before it plus the number there are is the number that goes here. Right? So that makes it order n time, k times. All right? And how much time we got left?
2 minutes.
2 minutes. We might finish this. All right. Here are loop invariant. Right? So now we did all these counts. Right? And this tells you that the first one is going to go here. Right? There are 5 things that are smaller than 1. Right? There's 17 things that are smaller than 3. So the first 3 goes in 17. Everybody buy that? So now we're going to go through. We're going to maintain that loop invariant. We go through and we put them where it goes. Where does the 1 go? It goes in 5. Good. Where does the 0 go? 0. Good. Where does this 0 go? How do we know that? We have to increment it, right? We have to maintain the loop invariant that the location of the next 0 goes there, right? So we increment that guy, and we increment this, right? So then the 6 goes, that one goes there. Everybody kind of get that algorithm? Good. All right. That was good enough. Let's go real fast. We're going to have one little last statement here. Come on, come on, come on, come on.
It's at the bottom.
Oh yeah, there's more on the next page, but right. So the point is that the running time in this algorithm is really fast. It's the number of numbers plus